So the last separating technique we look at is chromatography. Now, chromatography is an experiment you probably did in year 8. You probably don't really remember what it was for, you probably just remember that you got those nice pretty ink colours on bits of paper. It is actually quite a useful technique used by chemists because it allows you to separate a mixture of soluble substances from a solution. Because if you think about it, that's actually quite hard to get separated. We know how to get a solute from a solvent, so we can just evaporate the solvent away using evaporation. But if you've got more than one solute in a solution, it'd be quite hard to get them separate from each other. So chromatography actually helps us to do this. We separate different substances out by using chromatography paper and passing a solvent through them, and they'll spread out by different amounts on the paper. Now, it doesn't actually look that different from what you did do in year 8. There's a couple of extra terms we need to understand in terms of your GCSE chromatography. I'll look through notes in a second. We're going to just talk you through like the experiment itself with a wee diagram. So with chromatography, you generally have a bit of chromatography paper. Chromatography paper is essentially the same thing as filter paper, but just cut into a rectangle. You would normally draw a wee line at the bottom with pencil because you don't want the origin line to go up the paper with the ink, whatever you have in solution. You put a wee X where you're putting your spot, and then on the spot you will, maybe with a pipette or using a marker, whatever, you will put your mixture of different substances. That could be different inks dissolved in the solution, it could be different amino acids, different proteins, it could be whatever you want. You would spot it on that X there. To get the experiment to work, you then put your bit of chromatography paper into a beaker. And you will fill your beaker up partially with some solvent. Now, normally that's going to be water. An important thing is that you make sure the water level does not go above the origin line, this pencil line you've drawn on, because if it goes above that origin line, your ink spot, in this case, will be below the water line, so all the ink will just dissolve into the beaker of water rather than going up the paper. If you set it up like that, over time the water is going to soak through the paper. As it soaks through the paper, it's going to drag up some of the dissolved inks with it, and they will spread out because different inks will go up by different amounts. So if I show you the after picture, this is probably what it looks like after you leave it for a few minutes. So the water soaked up, so I've marked a wee line here, this is how far the solvent has got, the water's got. And as you see, your spot you had at the start has now separated into different individual spots as it's become separated through the chromatography experiment. Now, we've got a couple of terms to add onto this to help us describe what's going on in the experiment. First thing to maybe mention is this line that I drew on for how far the solvent has got, we'd normally call it the solvent front, which shows you the line of how far the solvent's got up the paper. This line at the start I mentioned before is the origin. You normally draw it with pencil to stop it moving up during the experiment. Now, we now have to address two more things. We give a name for the paper in the experiment, and not just it's called paper, it's got a specific term, and we give a name for the liquid or the solvent. We would call the paper in a chromatography experiment the stationary phase. And we would call the liquid, the solvent in the experiment, the mobile phase. The reason they've got those specific names is for any chromatography experiment to work, you have to have one thing which stays stationary, which means still, it doesn't move, and you've got one thing that moves through the stationary phase. The paper here is just sitting in the beaker, it's not actually moving, but the liquid is moving and soaking through the paper, allowing the ink spots to be separated out. So there's a couple of special terms we use to describe those. There is different types of chromatography experiments. We just stick to the paper one. So in this case, the paper is stationary phase, the solvent is the mobile phase. So if I just talk you through what you've got in your booklet now then. Chromatography, what's used for is to separate mixtures of soluble substances in a solution. Most commonly, probably at GCSE level, is inks, dyes and food colouring. At A level, you look at chromatography of things like amino acids, which make up proteins. A spot of the coloured mixture is placed on chromatography paper, and a solvent, most commonly water, is allowed to soak up the paper. The colours separate and move up the paper at different rates, so they're spreading out. A pure substance will leave just one spot, so that'd be something you could spot in a question. It might ask you, how do you know that substance X is pure? If it's only got one spot, there's only one substance there, it must be pure. This just is kind of repeating itself, we diagram there. These terms we talked about, the stationary phase the one where the mobile phase moves through it, the one that doesn't move, is the paper. The mobile phase, which is moving, is the solvent, or most commonly water. The reason that the spots actually separate out by different amounts is to do with how attracted they are to either the paper or the water. Because if you think about it, if you end up with a spot that's really stuck close to the origin where it started from, it's not moved that much. The reason for that would be it's really stuck to the paper quite strongly. So in other words, as the water moves through, the water's not able to drag it that far up the page. However, if you've got a spot which is right near the top, that must mean it's not very attracted to the paper. It's very attracted to the water because it's coming along with the water as it spreads through the paper. Substances that have a stronger attraction to the solvent, are more soluble in it, move more quickly and travel a long way out the paper, and the opposite will be true as well. The last thing you've got to look at in terms of chromatography is a little calculation you can do. And there's a calculation that scientists find quite useful. Why you might use this is as follows. If I was doing a chromatography experiment on a mixture of chemicals, and I'm not quite sure what the chemicals are, it would be quite useful if I could work out, just by looking at the position of the spot on the paper, what that chemical might be. Because there's reference tables you can look up for different substances that will tell you what specific substances will give you in their chromatography experiment in terms of how far they travel up. So you might think, well, that sounds good enough. All you do is just measure how far it's got from the origin line. It's not quite as simple as that, because as you might appreciate, every time you do a chromatography experiment, you're not necessarily going to let it run for the same amount of time. In other words, the distance it travels might be different in different experiments. What we're actually looking at is a ratio. If we compare how far your spot has gone up the paper and compare it to how far the solvent got up as well, that will always be the same, that ratio. So even if I only let the chromatography experiment take place for a few minutes, so it hasn't gone up very far, it will still have the same ratio of how far the spot gets up versus how much the solvent gets up. So the calculation we do to work out that particular key reference value for that particular compound is known as the RF value. RF stands for retention factor. You don't really need to know that. The calculation you do is distance moved by the compound divided by distance moved by the solvent in the experiment. And as I said, that should be the same for every single experiment of that compound. It doesn't matter how far you let it go up the paper, it's the ratio of the spot to the solvent. So that is a question that comes up in terms of them getting you to calculate it, and it will just involve you using either a ruler in the exam, or they might give you a wee scale drawn on your paper in the exam. It's nothing to be scared of. So for this particular experiment, I know it's a wee bit grainy, but it might ask you the question, here's a spot in the chromatography experiment, calculate the RF value for that for that spot. You need to measure two distances, the distance moved by the compound and the distance moved by the solvent. One wee pitfall is you never measure from the very bottom of the paper, you measure from the origin line where the spot started. So I would just get my ruler in the exam, measure from this origin line to that spot, 2.1 centimetres in this example. I would also measure from that origin line to the solvent front, in this particular example it's 2.8 centimetres. All I do is just divide it, do it the right way around. Distance by the spot divided by distance by the solvent, 2.1 over 2.8 gives you 0.75. You normally give it as decimal place, and you normally give it to two decimal places, so 0.75 would be your answer there. If you think about it as a wee kind of exam check, because with dividing ratios it's quite easy to get them the wrong way around, if you remember that your value should always be less than 1, in other words, your dot can never travel further than your solvent can, because solvent always ends up at the top. So if you divide that the wrong way around, your answer will become bigger than 1. So always remember, your final number should be smaller than 1. If your RF value is 0, means it hasn't moved, because you're dividing a 0 distance by another distance which is still 0. The same substance will have the same RF value in the same solvent. So that's the key kind of analytical thing you can use to work out what a particular substance is. So in your booklet now, you've got a couple of examples. So I'm going to talk you through the first one, and then I'll just show you the answers for the rest of them rather than going through each individual one in front of you. So what you'll need is a ruler and a calculator to do some measuring and calculating. Your numbers might not come out exactly the same as what I'm getting, because obviously different people's printers are different, but hopefully be close enough to your answers. Well, the RF value should still be the same though. So in this one, I might have to work out the RF values for these 3 spots. One my exam tip as well, obviously you might be thinking, well, where do I measure to? You should be aiming for the centre of each spot as a general rule. So this first one, I'm going to measure the distance travelled from the origin to the spot. So if I just look, that's pretty much exactly 1 centimetre for me here. And I'm going to compare it to the distance moved by the solvent. And if I look here, I make that 4.6. So to work out the RF value for that first spot, I would do 1 divided by 4.6, which gives me 0.22. 2 decimal places is normally enough. If I did the second spot, I'm going to do the side here a wee bit just so you can see a bit clearer. I make that 2.1. It's the same distance travelled by the solvent, that's not changed, just going to be 2.1 divided by 4.6, which gives me 0.46 for that particular spot. And then the final one, running over him here, I make that pretty much exactly 4 centimetres. So my RF value is 4, distance travelled by the spot, divided by 4.6, the distance travelled by the solvent, which gives me 0.87 as my RF value. So I'm going to pause the video now, work through the rest of them. If you've got in front of you, work them out as we practice yourself. So I've got the next couple worked out there. So again, just look at your final values, make sure they're kind of roughly the same as mine. For this second one, the bottom spot came out as 0.11, 0.5 divided by 4.6. Second spot 0.57, 2.6 over 4.6. Third one 0.76, which came from 3.5 divided by 4.6. Again, just be clear, maybe I didn't explain it clearly at the start. You can normally assume that your solvent line is given by that dotted line above the spots. Though probably in the exam they would label it. Third one, bottom spot 0.07, which is 0.3 over 4.6. 0.26 for your second one is your RF value, 1.2 divided by 4.6. Top one 0.87, which is 4.0 divided by 4.6. Well, this one is retypo, unfortunately lines missing, so we'll not worry about it for now. So that's pretty much it for chromatography. So just knowing your definitions of your stationary, mobile phase, solvent front, things like that. Knowing that how far spot travels up the paper will depend on how attracted it is to either the water, the solvent, or the paper. And then final bit is knowing how to do that wee calculation to check your chromatography paper, which is known as your RF value, which is distance travelled by a spot divided by distance travelled by the solvent. So we're going to round off this wee section on separating techniques with a wee summary table. Because whilst I don't think this may be the hardest bit of chemistry you've studied this year, it can be quite easy to mix these separating techniques up, particularly in the question where you're having to pick the correct technique for a particular mixture to separate. So it's going to give you a wee kind of analytical method to work out which one is most appropriate. So if they give you in the exam a mixture of an insoluble solid into a liquid, see how we think about that. That's a solid that's just sitting at the bottom of a liquid, need to get them separated. I would use filtration. If I had, in another scenario, a soluble solid dissolved in a solvent, I've got a bit of a choice now, so I can either use evaporation or crystallization, a very similar technique, or I can use distillation. And it really depends on what I'm trying to achieve. If I'm only interested in getting this solid back, I can just evaporate it. If I want the solid back but with nice crystals, I use crystallization. If I want the liquid back from that mixture though, I'll need to use distillation, because it involves heating the liquid off, evaporating it, but then condensing it again, so you use distillation there. If I've got, in this next scenario, I've got some liquids, but I've got 2 of them, so 2 immiscible, which means doesn't mix. Hopefully you remember that involves using the separating funnel. If I've got another 2 liquids, but this time they are miscible, which means they do mix, I would use fractional distillation, which allows them to separate out a wee bit better during distillation. Final scenario, if I've got a mixture of solutes, so more than one solute. Dissolved in a solvent, I would use chromatography to separate them out. So the key thing is understanding what each technique actually achieves in terms of what type of mixture it's able to separate.